Good morning. Today we will study about quantum theory of Raman scattering. What is Raman scattering? Raman scattering. What is Raman scattering? What is Rayleigh scattering? What is elastic collision, inelastic collision? What is Raman shift? What are Stokes? What are Stokes Anti-Stokes line? There are two theories. Actually, there are two theories to explain the Raman scattering. Raman scattering is explained by using two theories. One is quantum theory, another is classical theory, classical mechanics theory, quantum mechanics theory, classical mechanics theory. Okay. Now let us see. Let us consider a molecule. Let us consider a molecule with energy E. Okay. A photon of light, h nu, wavelength lambda, a photon of light h nu with the wavelength lambda, frequency nu, falls on a molecule, and the energy changes now. See, before collision the energy is E. After collision with the photon, the energy of the molecule changes E prime. Let us call the energy change E prime. After collision, the energy of the molecule. Okay, now it will scatter light. The molecule absorbs the photon and it will scatter light in all the directions, and especially the intensity of the scattered light is more intense in the direction perpendicular to the incident beam. This is incident beam, this is the scattered beam, 90 degree. At this angle, the intensity of the scattered light is maximum, although the scattering occurs in all the directions. Okay. Now, in this case, you see lambda equal to the wavelength. There are three cases. Lambda is equal to lambda prime. Another case is lambda prime greater than lambda. Another condition is lambda prime is less than lambda. So there are three cases depending upon the wavelength of the incident and scattered light. So you see C is equal to nu lambda. Nu is inversely proportional to lambda. Therefore, nu equal to nu prime. Here, nu prime less than nu. Nu prime greater than nu. Okay, because it is inversely related. Lambda C and nu and lambda are inversely the wavelength. Lambda is the wavelength of the light, photon. Nu is the frequency of the incident light. Nu prime is the frequency of the scattered light. Okay, the wavelength is the distance between two successive. The wavelength is the distance between the two successive trough or two successive crests. Okay, so lambda equal to lambda. Okay, now the energy of the molecule before the collision, and h nu, the incident light energy, equal to E prime plus h nu prime. H nu prime, because the energy is conserved. During the collision. Okay, now E is the energy of the molecule before collision. E prime is the energy of the molecule after collision. The molecular energy, each molecule has energy. Each molecule possesses energy. The molecular energy consists of electronic energy, rotational energy, and the vibrational energy. And also we have translation energy, but it is the translation energy is very small. Okay, now let us see case 1. This is called case 1, elastic collision. In this case, the collision is elastic because lambda equal to lambda prime. Okay, so nu equal to nu prime. In that case, nu equal to nu prime. Therefore, h nu equal to h nu prime. Therefore, h nu prime equal to h2. Then E equal to E prime. This is called Rayleigh scattering. This scattering is called Rayleigh scattering. And the other two are called Raman scattering. Case 2 and 3 are called Raman scattering. Also, it occurs due to inelastic collision between the incident photon and the molecule. Okay. Raman scattering is also called Raman effect. Raman spectroscopy. What is Raman spectroscopy? Raman spectroscopy is based on Raman scattering. After Raman scattering, Raman spectroscopy was developed. Okay, It is used to characterize a molecule, it is used to characterize a compound, etc. You know, but it is not due to absorption. Most of the spectroscopy are based on absorption spectra, absorption of light. We have already studied Beer-Lambert's law. It is not absorption spectrum, it is due to scattering. It is due to scattering of light. Okay, now let us apply the quantum theory to explain understand the Raman effect. How, why Raman scattering occurs, why these cases occurs. See, let us consider, for example, when the molecule, when the photon of energy falls on a molecule, it absorbs energy, or it without absorbing it emits. This is the case. There is no absorption of light. In this case, for example, you see, let us consider the vibrational energy levels of molecules. This is ground state, mu equal to 0, vibrational quantum number, mu equal to 1. We have seen in okay, already we have seen vibration spectroscopy, mu n equal to E, energy is En. Now you see, when the photon of light is observed, the molecule undergoes transition from E0 to En. It goes to highly excited state, highly unstable excited state, and from the excited state it emits light, that is scattered light. Therefore, if you look at it comes to excited state, not to the ground state. Here you see, this is the incident light, when the incident light and the scattered light, and the delta E, this is delta E0, En, therefore En is, it may be 5, 6 or 1 or 2, depending upon the energy of the incident photon. If the energy of the incident photon is high, then it will go to 0 to 10, 20, etc. If the energy of the photon is less, then it will be 5, 2, etc. So it is N. And from the excited state, it falls to first excited state, okay, not to the ground state. Here it falls to the ground state. Therefore, h nu equal to h nu prime. Okay, lambda equal to lambda prime. H nu equal to h nu prime. Therefore, lambda equal to lambda prime. Here, case 2, see the wavelength lambda prime, because the energy E naught minus En. Here E naught. This energy is more. The emitter. Therefore, the difference in energy is absorbed by the molecule. The difference in energy is absorbed by the molecule. Therefore, the wavelength is less. The wavelength is longer. This is opposite. For example, in the case of 3, the molecule absorbs the light. The molecule in the excited state, E1, that is E1 to En, and then from the excited state it falls from mu n to En to E0, ground state. Okay, if you look at this, see the energy difference. Here the energy difference. Therefore, this is the incident photon. This is the energy of the incident photon, E1 minus E. This is the energy of the scattered photon. The energy of the scattered photon is larger. Therefore, h nu prime is larger. Therefore, it will be this lambda greater than lambda prime. You see, lambda is greater than lambda prime. Okay. So, the case 1 is called Rayleigh scattering, as we have seen. The case 2 and the case 3 are due to Raman scattering because of absorption of light by the molecules undergoing vibrational transition. Okay. Similarly, you have a rotational Raman spectroscopy. In the case of rotational energy levels, the energy gap will be low. The energy gap will be less. Therefore, the incident photon frequency, the energy of the incident photon should be less for rotational Raman scattering, rotational Raman spectroscopy. Okay. Now you see, this is the Raman spectrum. This is the Rayleigh. This is due to Rayleigh scattering. This line is more intense because this occurs. The transition probability is very high, and also whereas in the case of this, it will be less, intensity will be less. On the other hand, this intensity is very less. Why it is very less? This question will be asked in various competitive examinations, because the transition in the case of 3 from E1 to En, okay, the vibration level 1 is less populated. See, this is especially the ground state is more populated. The ground state, the molecules will be in the ground state, lowest energy state, that is stable. Okay, so very few molecules, here a lot of molecules will be there. Okay, here very few molecules will be in the excited state. Therefore, the line will be less intense. The line will be this line, anti-Stokes lines are less intense, because the first excited level is less populated compared to the ground state. Therefore, this line is more intense and this line is less intense. Okay. So now let us see what is Raman shift. You will be asked problems, because E plus H nu equal to E plus H nu equal to E prime H nu prime. Then therefore you interchange E prime minus this side, okay? E prime minus E, and then H nu, you will bring this here, H nu minus H nu prime, therefore H is common, H nu prime, okay? Therefore E minus E prime minus E equal to H is delta nu. This is delta nu. The delta nu is the Raman shift. The delta nu is the Raman shift in terms of frequency, of incident photon and scattered photon. Okay, and C is equal to nu lambda, that is nu equal to C by lambda. 1 by lambda is called wave number. In most of the spectroscopy, in vibrational, rotational spectroscopy, it is expressed in wave number, not in the terms of wavelength, not in terms of frequency. It is expressed in wave number. So in problems they will ask, they will give in wave number only. Therefore, nu equal to 1 by C nu bar, on substituting in this expression here, nu, therefore the C, where C is the velocity of light, and nu is the frequency of the light incident photon, and lambda is the wavelength of the incident photon. And therefore, on substituting this expression delta nu bar, the delta nu bar is the Raman shift in terms of wave number. Delta nu is the Raman shift in terms of. Therefore, you can use this formula to H Planck's constant, C and you can calculate the Raman shift. They will ask several problems based on this formula, and also they will ask why anti-Stokes lines are less intense, because the excited state is always less populated compared to the ground state. You need to explain that. Thank you for watching.